For this week, doing volumes by known cross sections. This topic directly builds off of areas between curves. So you really can't do this topic unless you really are honestly comfortable with area. The short version of this is basically like the past 2 days we've been looking at area, which is a two-dimensional measurement. It's flat, and we are moving now into kind of like this three-dimensional world. Like clearly that's what the world is, 3 dimensions. How can we use calculus to find the volume using our knowledge that we can use calculus to find the area?
Who's late? Sorry.
Ian,
I might be joking.
huh?
I won't be late tomorrow.
Okay. You should get to your Spanish class.
You guys go get water.
You made me so nervous I spilled.
So, things that I want us to be looking at when we're talking about doing these volumes. We do need to kind of think about like what these are look like. So I want to be first off and honest, like you don't have to like visualize these three-dimensionally. Some people just like can, like they're very good like spatial awareness, like they can imagine what these solids look like. Then I honestly have some students who are like, Mr. Brown, I have no idea what this looks like. Doesn't really matter as long as you know how like the solid is built. I am going to go ahead and show you, I have this GeoGebra page that will at least give us an idea of what it looks like and kind of see where we are going with this. This is linked to in your OneNote as well. The GeoGebra 1 is actually a little bit better one to look at. But to preface what we're looking at for this one is similar to what we were doing when we were talking about areas. We're going to have like some region bounded by two or more graphs. Like on this one, it was like an x squared function and a square root function. This region, you want to imagine, instead of acting as an area, when you're looking at your paper or looking at your screen, you're doing a bird's eye view of a three-dimensional solid. So this is like the foundation of the solid that you're looking at. And coming out of the page to you is the three-dimensional part. How these problems will be described is they'll tell you like what each cross section look like. So if you kind of imagine like, I don't know, like a loaf of bread, and you're going to pick up one slice from the middle of the loaf of bread, that would be like a cross section of the loaf of bread. So like this one, what I did, this is like, again, the foundation of it. This is the bird's eye view. Obviously, we can't do this easily when we're working in 2 dimensions, but we can imagine like I tilt the graph. Now we can see visually the cross section. This will be an example where the cross section forms squares, and we'll look at different examples. Sometimes we'll say the cross sections maybe are equilateral triangles instead. It could be circles. It really could be any type of geometric shape. I'm gonna go back to the square one because I like the way that one looks. Again, you don't need to know like what this shape looks like. Thankfully with technology, I can kind of show us what it looks like. But this is basically like some weird three-dimensional figure. I'll let it just kind of spin, that we're going to be using calculus to find the volume of. Again, it is kind of based off of area, but instead of just dealing with area, we have like this three-dimensional figure built on that region. So before we can kind of get to the calculus, there are going to be some things that we have to do first. And the first thing we need to do is just to make sure we remember all of our basic geometric formulas. There's some common ones that the AP exam will use, and that's what I have on this handout. I do want to preface this and say that some people just like memorizing these formulas I give you. Some people are like, I have too much stuff to memorize already, so let me just remember how to come up with those formulas every time I do a new problem. For me personally, I tend to just memorize it, but I've definitely been doing this for too many years, so like I just know these formulas. I've been doing it so often. But what you want to imagine with these is, so when I have these different cross sections, like when I say a square, when I say a rectangle, you're imagining that's like the slice of bread that's sitting on top of that surface. That's going to be the thing that's coming out of the page towards you. What I have in red labeled with B is going to be what's sitting on the base. That's going to be sitting on that foundation. That's going to be what's laying on the region that you're looking at. We are often going to want to write the formula, the geometric formula, in terms of the base. So like the square is easy. If I say that a square has a side length of B, what is the area of that square going to be? B squared, easy enough. We know area is length times width, so if it's a square, it's just gonna be B squared. Same thing for a rectangle. We know the area of a rectangle is base times height. They can give you all sorts of dimensions for the rectangle. Sometimes they say like the height will always be half the base, or maybe the height is always 2 more than the base. You just wanna like read the problem. Kind of chose an easy one. The base is B for this specific rectangle. The height is 3, so we just have basically like base times height. Again, the main idea with these is we're going to need to be able to write some formula representing the area of a slice of this kind of irregular 3-dimensional shape. The next common type of slice that we see is going to be an isosceles right triangle. An isosceles right triangle is going to be your 45, 45, 90 triangle. And you will have to be kind of careful, depending on the problem we worded, and be very clear about where that triangle is being sliced. Like if you have an isosceles right triangle, it could be so that you have one of the legs as the base sitting in that area. Or it could be an isosceles triangle where it's the hypotenuse sitting on that base. But again, we still want to be able to write the area of that figure in terms of that side I have labeled B. So I'm thinking about a triangle. We know the general formula for a triangle is 1/2 base times height. The isosceles right triangle, when B is one of your legs, is going to be the easy one, because if one leg is B, the other leg is also B. So what would be a formula we could use for that type of isosceles right triangle? 1/2 B squared, right? 1/2 base times base, since they're the same. So the area formula would be 1/2 B squared. So it's kind of like a simplified version of the area. What about if I change it to where that triangle is laying on its side and its hypotenuse I'm now labeling B? What will be the length of each of the legs then? And you might need to remind yourself if it's an isosceles right triangle, that's a 45, 45, 90 triangle. In a 45, 45, 90 triangle, each leg is the same, and the length of the hypotenuse is the length of a leg times the square root of 2. So if I'm telling you that the hypotenuse is B, what will be the length of each of the legs?
B over root 2.
B over root 2. So again, that's what you have to do if you're trying to derive it yourself. But again, it might be easier for some of you just to memorize the formula. What will be the area of this right triangle? It's still going to be 1/2 base times height, and the base times height will be perpendicular, so it will be the 2 legs. So 1/2 B over root 2 times B over root 2. Well, 2 times root 2 times root 2 is just 4. So an easier simplified formula to just memorize, if you don't want to derive it each time, will be 1/4 of B squared. So those are the 2 formulas you want to know for an isosceles right triangle. The other 2 common ones I see are an equilateral triangle. So like again, those slices on this 3-dimensional figure might be an equilateral triangle, and then also a semicircle. The area of an equilateral triangle, we can derive a nice clean version for the area, because an equilateral triangle is basically 2 30, 60, 90 triangles sitting side by side. If you need the reminder, a 30, 60, 90 triangle, whatever the short leg is, the short leg times the square root of 3 gives you the longer leg, and twice the shorter leg will give you the hypotenuse. So if I want to figure out the area of this entire triangle, I basically do need to figure out what the height of that triangle would be. Well, if the entire side of this equilateral triangle is B, splitting it in half for that short leg would just be B over 2. Well, if the short leg is B over 2, what is the height going to be? Just root 3 times that, so root 3 B over 2. Hopefully those numbers look familiar. This is kind of where the whole unit circle comes from anyways. Then again, what is the area? You're doing the area of the entire equilateral triangle, which is 1/2 base times the height. Simplifying that to have an easier formula that will be useful to us to use. 2 times 2 in the denominator is 4, with a root 3 in the numerator, and B squared. That will be the area of an equilateral triangle given some side B. And then you have the semicircle. again with the base of B being that bottom side. Semicircle is half of a circle, so we know the circle is pi r squared. Half of a circle would be 1/2 pi r squared. If B is that bottom side, then a semicircle will be 1/2 of pi B over 2 squared. Simplifying that, this is one that I definitely recommend memorizing because it does show up a whole lot. The area of the semicircle, essentially in terms of its diameter, we have 1/2 over 2 squared would be 4, so we have over 8. There's a pi involved, and then B squared. That will be the formula of a semicircle in terms of its side B. Now again, why are we kind of talking about all these geometric formulas? It's going to help us actually find the volume because area is directly related to volume. How is it related to volume? I'm going to go off to the side and we'll kind of see how it is related. From geometry, so in many ways, a lot of the stuff we do in calculus is just built on stuff that we've already done in other math classes. From geometry, you learned what the volume of a prism is. Anyone remember the formula you learned in geometry about the volume for a prism of any base? And the formula you learned, volume is the area of the base times the height. That's when we have like the area of a rectangular prism is like length times width. That's the area of the base times the height. Area of the cylinder, pi r squared, area of the base times the height. And in calculus, we can basically take this geometric formula that we learned in geometry and turn it into a calculus formula. And where the calculus formula is going to come from, so these are volumes by cross sections. You're first, instead of going to find the area of the base, you're going to find the area of a slice. Or cross section, but I think it's easier just to think of this as slices. Well, what's going to be the volume of a slice? Think of it as kind of like a slice of bread. You have the area of like the face of it times the depth of it, which is going to be similar to us for height. To kind of convert this into some calculus stuff, when I say depth, that can be one of two things. If I have a slice that's going up and down, that's going to be a really tiny change in the x value. Or if I have a slice going left to right, it could be a really tiny change in the y variable. So what this would represent, that would represent the volume of a slice, of one slice. Where the calculus comes involved is this is a volume made up of a whole bunch of slices, starting with one side of the interval, ending at the other. How in calculus do I represent adding up a bunch of slices? That's where the integral is going to come into play. So literally, volume is the integral of area, and we'll have some limits of integration that will come from directly like we did with the area. How do we determine if it's going to be dx or dy? The exact same way we did area. So if your slice is going from top to bottom, you're going to do a dx problem. If your slice is going from right to left, then it's going to be a dy problem. These problems of volume by cross section are literally just like area with like one extra step. So let's look at the first example and then we'll kind of see where we're at in terms of questions. Here's how these questions will normally be worded. And we'll do this one without a calculator. So it says region S is bounded by the graph of y is equal to 6 minus 2x, y is equal to 0, and x is equal to 0. And then the key information we're going to focus on, S is the base of a solid. So once you graph it and see that region, that's like the foundation, that's the bottom of this three-dimensional figure. And cross sections, again, you kind of imagine them coming straight out of the page towards your face. Those slices are perpendicular to the x-axis. That's important because that's going to tell you whether we're doing it in terms of dx or dy. And then it also tells you what shape those solids are. It tells you that the shape of that solid is a bunch of semicircles. You do these problems just like you do the area problems. Do you want to have some sort of visual so you can kind of figure out top to bottom or right to left? Since y is equal to 0 and x is equal to 0 are boundaries, I know I'm going to end up in that first quadrant. Y equals 6 minus 2x. That's just a line with a slope of 2 and a y-intercept of 6. Again, I'm just going to do a sketch. I know it has a y-intercept of 6 and a slope of 2, so it is decreasing. And then the region that I'm looking at is basically this kind of triangle shape, not kind of, it is a triangle shape. That's intersecting at 6 on the y-axis. Since it's bounded by the x and the y-axis, it is also starting at 0 for both the x and the y-axis. Probably also want to find the intersection point down here. Easy enough, that's basically the x-intercept. So x is equal to 3 there. So we have the region, I'm going to kind of highlight it in. Again, you don't have to readily visualize what this is, but you want to imagine you are looking at a bird's eye view of this three-dimensional figure. It tells you that if you took out a slice of this, and if you cut perpendicular to the x-axis, so here's just a representative slice, it looks like a vertical bar, but if I were to go and be able to reach in and pick up that slice that I just drew would be a semicircle, where the base is right here, would become the diameter of a semicircle. Again, you don't have to know what this looks like. It kind of looks like, again, I'm terrible at drawing in 3D, but you have like a semicircle that's really large, and it's kind of tapering to a point, and it's kind of like a, I don't know, like a little tunnel that kind of goes down to a single point. Again, don't have to know what it looks like visually, especially my terrible three-dimensional drawings, as long as you can kind of figure out the pieces of everything you have. So then it says write the integral. Do not evaluate it. And when I do these problems, like with practice, you can just jump straight to the volume. To start off, I'm going to kind of do it as like a 3-step process. The first thing I want to do is to identify that b value. And we're going to find the length of b. So in this case, that b is representing the diameter of a semicircle. It's going up and down. So think back to area. When we go up and down, it's going to be the top function minus the bottom function. What's the top function? The top function was 6 minus 2x minus the bottom function. Could leave it off because technically what is the bottom function? The bottom function would be 0. Should have asked this before I wrote that down. How did I know this was going to be a dx problem instead of a dy problem? Vertical. We're connecting top to bottom, so it has to be dx. If you connect right to left, it would have to be dy. So that's the first thing you do. Then we're going to write the area in terms of the base. Why do we want the area? Because we know the integral of area yields volume. This is a semicircle, so you either use a memorized formula or you have to derive what the formula would be in terms of b. I have it memorized, it's that last one we wrote down. What's the area of a semicircle? The area of a semicircle is pi over 8 b squared. Let's go ahead and put that in terms of x now. What was b equal to? B was equal to 6 minus 2x minus 0. Again, I could leave that 0 off if I'm just using it as a placeholder, squared. So I had the base, I had the area in terms of the base, then big calculus fact, how do we get to volume? Volume is literally the integral of area. What is the area? Pi over 8 b squared for the semicircle. Again, don't think it's always pi over 8 b squared. This is just for the semicircle. We are integrating with respect to dx, and then what numbers do I need to put on my integral sign? 0 to 3. So in terms of dx, this area starts at 0, ends at 3. And again, what that means is you're adding up an infinite number of slices going across the page, which is going to give you the volume. Doesn't ask us to evaluate it, thankfully, so that would be the final answer. questions on that? Yes, Donna?
Like, why is B that formula, the top minus the bottom?
You want to think about it like we want to find the length of B. And for those at home, the question was why is B that formula? So what is the length of B? It's like this y value at the top minus the y value at the bottom. What's defining the y value? The function is. And you want to put a function there because of course, as like B moves across, it gets larger and smaller. So we're putting basically B in terms of x.
And so like, it doesn't, like B could be anything from the top to the bottom.
Yes, so like this one just happened to be 0. I'll do another one later where that's not a 0. You have a question, Vince? Same question. Any other questions from those of you at home?
Mr. Ryan, I have a question.
Yes, go ahead, Liam.
If we were to find the volume of the whole thing, we would find the integral of the top minus the bottom.
Yes.
And then find the integral of that.
Yeah, well, define the antiderivative if you had to. I would clearly drop the 0, but you would have to FOIL this out and then just use the power rule. I will say most of the time, even on the AP exam, a lot of these questions are just like the setup, but don't evaluate. Go ahead and try this one for me. I took it the same region, and I literally just changed one thing. I kept it with the same cross-section, so the cross-section is still semicircles. The only thing I changed is the way that you are slicing, which does change how you do the entire problem in many ways. So now instead of slicing up and down, you're slicing left to right. But we are still doing semicircles. So again, you don't have to clearly show like what B is equal to, what A is equal to. If you are able to just jump straight to the volume, many of you can. I expect many of you to be able to. But again, if I'm building my answer, we first need to figure out what the area is in terms of either X or Y. If my cross-section is now perpendicular to the Y-axis, is this going to be a dy problem or a dx problem? dy, and again, I know it's dy because the way I connect the sides will be from the left into the right. So it would be in terms of dy. So I do want to make sure that everything is in terms of dy. So what is the length of b? The length of b would be the right function minus the left function. Again, you could have left off that minus 0, kind of just reminding you that if it wasn't 0, you would have subtract off the left function. We're still dealing with semicircles. What's the area of a semicircle? The area of a semicircle is pi over 8 b squared, when b is representing the diameter. And then we know that volume is the integral of area. So we're going to integrate the area formula. What is the area formula? Pi over 8 b squared, and we're doing this with respect to dy. What was the b? 6 minus y over 2 minus the 0. Do you want to make sure, since this is an actual volume, we have numbers on our integral sign? What numbers are going to go in the integral sign for this problem?
0 to 6.
0 to 6. So we're starting at 0 and then ending at 6 on the y-axis. Again, big idea, if I could summarize anything from this topic, is in calculus, volume is equal to the integral of the area with either respect to dx or dy. Questions on that one? All right, 2 more, changing the region up. Try that one for me. Again, treat this one like an area problem when you're starting it off. Definitely need to figure out what the region is. You should be able to graph those by hand. do need to figure out where that region is starting at and ending at, so you probably need to algebraically find the intersection points. And then figure out what b is. Are you doing it in terms of dx or dy? And then once you figure out b, you want to write a formula for the area in terms of b. You want to look at what shape you're using. This is a little bit easier because the shape is just a square. And then your final answer, volume, is the integral of a slice in terms of dx or dy. So try that one, and then I just have one more after this that's going to use that same region. So if I'm looking at this one, we have two quadratics, and again, I would expect you to know how to graph both of these. We have 9 minus x squared, so it's intersecting at 9 on the y-axis, but facing downward. X squared plus 1, crossing at y plus 1, opening upwards. So we can see this region I have highlighted in yellow. Again, that's the foundation of the solid that's coming straight out of the page to you. Cross sections are perpendicular to the x-axis. So that tells me I'm cutting up and down. Automatically knows it's going to be in terms of dx or dy. Dx, so we're connecting top to bottom, so it is going to have to be a dx problem. And that b is basically the base of a square. So like if I can reach in and pull out that base, it will be some slice in the shape of a square. Since we're cutting up to the top, we're going to do the length of b, which is going to be the top y minus the bottom y. So I have top minus the bottom. Could simplify it, but just leave it like that. It says it's a square, that's the easy area. What's going to be the area of the square in terms of b? Simply b squared. And so then I know that volume is the integral of area. So area is the base squared. What was the base again? 9 minus x squared minus x squared plus 1. We are in terms of dx. Since we're in terms of dx, I want to know where this is starting on the x-axis and ending on the x-axis. So I did find the intersection points. It's starting at -2 and ending at +2 on the x-axis. So we're integrating from -2 to +2. Thankfully, it doesn't ask us to evaluate it, so we can leave our answer like that. Questions on that? Hopefully that feels easy. Like honestly, if you're good at area and cross sections, you can kind of see it's just like a little bit extra work. The one question where I see sometimes students mess up on is something like this very last one that I want to do, where I have region T, same region, bounded by the graphs as y equals 9 minus x squared and y is equal to x squared plus 1. I'm going to draw the region real fast, but we actually don't need it for this particular problem. And what makes this one tricky, so if we're reading along it, it tells us that there's the base of the solid. It tells us that cross sections are again perpendicular to the x-axis. Since we know that it's perpendicular to the x-axis, we still know that this is going to be in terms of dx. But then the weird part is if you're looking at this question, so it says T is the base of the solid for which cross sections are perpendicular to the x-axis, they have an area of 4x squared. So it didn't tell us like what shape these cross sections are, but don't overthink it. They're literally already giving you the area formula in terms of x. Well, how do we get to volume? We know that volume is literally just the integral of area. So if you're doing this one, don't need to figure out what B is because they've already given you the area in terms of x. What is that area? Area is equal to 4x squared. How do I move from area to volume? We know that volume is literally the integral of area. What is area? 4x squared. Do just need to figure out what numbers go on the integral sign. Well, this is in terms of dx. It's going to be those same numbers we found before, integrating from -2 to +2. I sometimes see students for this one, they want to like try to plug in some like top minus the bottom and things like that. But how I kind of interpret this is they've already figured out what B is, plugged it into whatever the area formula is, and simplified it for you. So like the B is already kind of built into the area there. Questions on that one? That's like the only like exception there really is for cross sections. When they don't give you the exact shape, they're just going to give you the area directly. Questions? All right, so I am done. What I want you working on now is a little bit of a shortened period. How much longer we got? A little bit longer. So homework you should be working on. Homework 1 again is the big one. That's the one dealing with area. That's like the foundation for the entire unit. Definitely finish homework 1 before you move on to anything else. The homework I'm assigning for cross sections you'll like. It's just number 71 and 72. I will say for these, you only need to worry about setting up, not evaluating. The answer key does have it as evaluating, but honestly at this point, if you can't evaluate an integral, then we're in trouble. So I just want you to see setting up for homework number 2. Your quiz is on Friday, and that quiz is only going to cover areas between curves and then cross sections. There is an optional homework 3. Again, it's completely optional. I'm not assigning it, but you can kind of think of it as like a practice quiz and kind of get ready for that quiz. But I'm not going to assign it just because honestly, if you do homework 1 and 2, I think you'll be fine for the quiz. But I know some of you do want to do like a little bit of extra practice, and that's going to be the optional homework 3 you see. So I'll go ahead and get started on that. Again, homework 2 is just 71 and 72. And it shouldn't say just, there's like part A, B, C, and D for both of them. But again, I just want you to set it up, and that's it. So that concludes like the live portion of class. Definitely hang back if you have questions. Tomorrow is going